in all our previous classes, what was the talking point? The talking point was this, that the individual molecules velocities cannot be calculated. Therefore, we have an equation which gives us the distribution of velocities. Now, as such, the Maxwell-Boltzmann distribution law doesn't give you the values of velocities here, any type of velocities basically. What is Boltzmann distribution law? It is a distribution function, like I told you. Like we have discussed this at length. It's a distribution function. It only tells us if we consider a velocity value, or to be precise, if we consider a small range, if we consider a small range of velocities, if we do that, it only gives us what is the number of molecules possessing that v plus delta v velocities. Is it not? Example, using distribution function directly, if you cannot calculate any velocities of the gas sample of the molecules, so that distribution law is like a source from where you can derive many other expressions. And today we are going to look at the actual velocity terms. For example, if I ask you to calculate the velocity of nitrogen at 25 degrees Celsius, which formula do you use? You cannot directly use a distribution function. It doesn't give you the value of velocity. Therefore, we should use the distribution function or the Maxwell-Boltzmann distribution function. And then, since it's a differential equation, we will integrate it under different conditions and get answers. And those answers will be the actual velocity formulas. So when we do this exercise, in fact, we can arrive at 3 different types of velocities, right? Of course, one can still question, what do you mean by 3 different velocities? A gas molecule has only one velocity, right? But why we are looking at 3 different velocities? Because, this we have focused a lot of times that we can never calculate velocity of an individual gas molecule, right? Therefore, we will calculate collective velocities. So when these collective velocities are calculated, we get different type of statistical terms. Simple. So what are these? Actually, these are statistical terms, what we are going to get further, that are types of velocities. So these 3 types of velocities are the ones which are commonly used to calculate the velocities of a gas sample. We can never calculate the velocity of an individual gas molecules. Please, I'm repeatedly telling you this part. We can always calculate the velocity of a gas sample. Okay. So probably, if you are asked to come up with your own way of describing a velocity, what type of velocity would you use? Since, for example, individual molecules cannot be calculated, definitely an average velocity can be calculated, right? Like that. So average velocity is a term, actually a practical term, statistical term, average velocity. So what is an average velocity example? You just have to take the velocities of individual gas molecules and divide by total number of gas molecules. That becomes the average, the arithmetic mean. But can we do this actually? No, because individual velocities cannot be experimentally calculated. So how do we now calculate average velocity? So generally, how do you calculate averages? For example, if what is the batting average of a batsman if he has played 100 matches? He will take the runs he has scored in every match divided by 100. Or if he has played some 75 matches divided by 75. So that's the way you calculate average. But here the direct calculation is not possible because individual gas velocities we don't have. So what's the point now? So at this point, actually our Maxwell-Boltzmann distribution law becomes very significant, because when you derive average velocity expression from the distribution law, you see that individual velocities are not there at all. Rather, the average velocity will be calculated in terms of other physical quantities like temperature, like molecular weight, like for example, the real gas constant, like that. So this is actually a very, very wonderful application of Maxwell-Boltzmann distribution law. Anyways, now let us just look at the definitions of these three types of velocities. One type of velocity is the most probable velocity. Okay, most probable velocity is at which the most molecules in a gas travel. It's the velocity of the most number of gas molecules. Okay, so most probable velocity, actually this can be derived from your Maxwell-Boltzmann distribution law, which we are going to do in the next class. I just want to introduce you to the different terms of different types of velocities. So that's the formula. Most probable velocity is equal to square root of 2RT divided by m, where m is the molecular weight of the gas molecules, or the formula can also be square root of 2kT divided by small m, where m is the mass of an individual gas molecule. Anyways, we will look at this when k should be used, when r should be used later. But look at the expression for most probable velocity. Anyways, once again, what is most probable velocity? It's the velocity maximum number of molecules are possessing in a gas sample. Most number of molecules are possessing in the gas sample. And look at the expression. You can just calculate that simply by knowing the temperature and the molecular weight of the gas. And how did we arrive at this expression? By using our Maxwell-Boltzmann distribution law and differentiate, decide, since it's a differential equation, the derivation will do. Anyways, so very handy equation. Most probable velocity is directly calculable using this formula. Now we will come to one more term called root mean square velocity, sometimes called RMS velocity, also abbreviated as RMS velocity. What is this root mean square velocity? Okay. Anyways, okay. Root mean square velocity is defined like this. It's the square root of what? Square root of mean of the squares of the velocity of individual gas molecules. So if V1 is the velocity of a gas molecule, V2 is the other gas molecule, V3 is the velocity of the third gas molecules. You just have to take the velocity, square them, and then take the averages of all the velocities, velocities of individual gas molecules. But the definition doesn't seem very straightforward, right? Why do you have to square and then take a square root? Essentially, is it not? Because if you square and take a square root, what do you get? The actual number. What's the square root of 2 square? 2. So why don't we directly write 2 instead of writing 2 as square root of 2 square? That's the point here. In the RMS velocity, although root mean square velocity is takes an indirect approach in its calculation formula, but it has a lot of significance physically. It has a lot of physical significance. Why? Why? Because see, if we directly take the average of all the velocities, there is a danger. What is the danger? The average may come to 0 sometimes, or very low value, which is much smaller than the actual velocity of the gas molecules. Why? Why? Because, as you know, the velocity is a vector quantity, unlike speed, which is a scalar quantity. Why is while we are handling vector quantities or doing calculations with vector quantities, and you take an average, that is not the answer will not give you the actual picture. Why? Because the vector quantities also have directions. For example, now I choose 2 gas molecules like this, which are moving in opposite directions, equal velocity. Example. So let me choose this molecule which is moving in this direction, whereas the other molecule which is moving in the opposite direction. Let us think that it's with equal velocities. So what is the velocity of this and this? If the velocity of one molecule is v, the molecule in opposite direction equal velocity is minus v. So you take an average of V plus minus V divided by 2, you'll get average is equal to 0. So to avoid these things, to avoid the cancellation of velocities with their signs, because of their signs, we have invented this trick. What is that trick? Mathematical trick. What is that? How to avoid a negative number? Yeah, you square it. Is it not? So what's the square of minus 2? 4. What's the square of plus 2? 4. So if you take, for example, velocity is v and this is minus v, instead of taking direct average, you take the average of these squares. So v square plus minus v square. So v square plus minus v square will give you what? How much? 2v square. 2v square divided by 2. So 2 cancels. The answer comes to v square. The mean comes to v square. But then you have square right. So now you put a square root. Then that becomes square root of v square. You still get v. So if we had directly taken the mean, we would have got average velocity is 0. But in this method, we are getting average velocity as v, some finite value, is it not? The same thing is done for calculating the root mean square velocity. First, the individual velocities are square, and then the average is taken, and the answer is further square rooted. So that's what. This is one more expression for RMS velocity: square root of sigma v square divided by n. What is v? V is the velocity of individual gases. But again, since the velocity of individual gases cannot be calculated directly, we use an average velocity here. Instead of sigma v square, you can also use sigma v average square, like what I have written here. See, whenever, particularly in statistics, you get a term with a horizontal small line above it, it means it's mean or it's an average value, right? So just v and v dash is an average. So again, you can use your Boltzmann distribution law and derive the expression for VRMS, root mean square velocities. It comes as square root of 2RT divided by m. Square root of 3RT divided by m. The other form of the equation is square root of 3 kBT divided by small m. So now what's the difference between these two equations? This equation has a constant r, real gas constant, whereas this equation has a constant k, which is Boltzmann constant. So what are these real gas constants and Boltzmann constants? Actually, they are same. Boltzmann constant and real gas constant, except real gas constant is a constant when we consider for our calculations 1 mole of a gas, whereas Boltzmann constant is a constant when we consider single gas molecule. Therefore, real gas constant divided by 1 mole's Avogadro number will give you always the Boltzmann constant. So Boltzmann constant and real gas constant are always interconvertible. This is the equation. Boltzmann constant is equal to real gas constant divided by Avogadro number. So in nutshell, in summary, what can we tell? That Boltzmann constant is just a real gas constant per molecule. R is per mole, K is per molecule. So when you are solving problems, either in the question you get the molecular weight of the gas or the mass of an individual gas, anyways you can still solve this problem, or still you can find out the root mean square velocities. And the last type of velocity will be the average velocity, and there is no much complication in this definition. It is simply the average of velocity of all the gas molecules. And how to get it out from the equation? Average is equal to square root of 8RT divided by pi m. See, whenever in these equations we use capital R, real gas constant, we take the molecular weight of the gas. Whereas if we use K, we take the molecular weight of an individual molecule, right? Single molecule. So if we can represent these different types of velocities on our curve, Boltzmann distribution curve, what are their positions? See, most probable velocity is the velocity possessed by maximum number of molecules. So where on the y-axis, what are you plotting? Number of molecules. So maximum number of molecules means the highest point on the y-axis. So this is the highest point of the y-axis. Is it not? There is no more values beyond this because this is the peak. So this is the highest point on the y-axis. Most probable velocity is simply the velocity corresponding to this highest point. So that will be the most probable velocity. Now the average velocity will be around, average velocity is a bit lesser than the most probable velocity. Therefore, it will be around towards the right of your, or right or left, doesn't matter, of your most probable velocity. And root mean square velocity is further, see, average velocity and root mean square velocity, both are averages only. What is the difference? In the root mean square, we have taken the average of the squares and then square rooted it. So both are average velocity. That's what I told you. This is all the statistical approach here. In statistics, what do you do? When you have a large data and to make some meaning out of data, you start analyzing the data, right? So how to analyze the data? You have to take some averages of that, or you have to do some calculations on that, statistical calculations. So different types of analysis or different types of statistical terms are coined. Average is a statistical term basically. Root mean square average is also a statistical term. See, root mean square average is not just limited to velocities average. It is a bigger term used in statistics. For any quantities, you can do that. Root mean square average is a very strong term in statistics, applied in many other cases, not just velocities cases of gas molecules. Root mean square average. So that's it. Therefore, what are the three types of velocities we have defined today? Most probable velocity, root mean square velocity, and the average velocity. And we know their formula even. So RMS is equal to, CRMS is equal to square root of 3 RT divided by M. Average is equal to square root of 8 RT divided by M. And this is square root of 2 RT divided by M, mean square, most probable. So if you look at these things, they almost look similar, right? And since they're velocities, you can always take a ratio of these velocities. So when you do this, and looking at the formula, you can tell which velocity will be having the highest value, most probable velocity. Is it not? So most probable velocity is equal to 8 RT divided by M, followed by average velocity, followed by RMS velocity. Same terms can be cancelled, right? When taking a ratio. So if you cancel R, T, T, and capital M, capital M, capital M, these things remain. Square root 2, square root of 8 divided by pi. You cannot cancel pi because there are no pi's here. And then square root of 3. And what are these? These are all numbers. Square root of 2, square root of 8. Pi is also a number. So you get as 1.414, 1.596, 1.732. So you can arrive at this relationship, a very important relationship. Most probable velocity is to average velocity is to RMS velocity is equal to 1 is to 1.128 is to 1.224. So what's the use of this relationship? You can simply calculate the two unknown velocities if one is known. So if I give you the value of most probable velocity, then multiply by 1.128, you will get average velocity. Multiply by 1.224, RMS velocity. If I give you RMS velocity and ask you to calculate most probable velocity, divide by 1.224, like that. So a very handy relationship, a very useful relationship, at least for solving numerical problems. This is the relationship. I think I've explained to you the different types of velocities. So in fact, in our next class, we will solve numerical problems on this. So in our whole discussion, I haven't solved a numerical problem yet. So next class, I will reserve for solving numerical problems as well as deriving an expression for most probable velocity from Boltzmann equation, Maxwell-Boltzmann equation. That's what I told you, right? That can be used to derive velocity terms. How is that done? With one example, with most probable velocity, we are going to see average velocity derivation and root mean square velocity derivation is not required. Okay, fine. Not required from your syllabus point of view. So, okay.